we have seen the definition of an integer program for the vertex cover problem. Now, I want to discuss a related linear programming formulation. What is an integer program in general? The general form is as follows: minimize or maximize an objective of the form c1x1 plus c2x2 plus cnxn, subject to the constraints such as a11x1 plus a12x2 plus a1nxn greater than or equal to b1 for the first constraint, and a whole set of, say, m constraints. In this course, all of our problems will be modeled by integer programs where you can add the constraint that for every I, variable xi must be between 0 and 1. Finally, for every I, vertex I must be an integer. An integer, that's why it's called integer programming. So we have this perfect integer program for vertex cover. If only we could use an algorithm for solving integer programming, we'd be done. But of course it's not possible. Integer programming is NP hard. Why then? Why are people so interested in integer programs? Because they provide inspiration, they provide initial tools to use to design better algorithms for related problems. In particular, let me show you a related linear program. This linear program is the same as the integer program, minimize the same objective with the same first constraint with b1, same second constraint, same last constraint, except for the last line. xi that no longer has to be an integer. Xi now is just any real number. With this apparently small, apparently harmless modification, suddenly the complexity of the problem changes. Linear programming can be solved in polynomial time. This was discovered about 30 years ago, and since then, linear programming has been a basic tool for the design of many, many problems, many solutions for combinatorial optimization. There are two ways to present a linear program. One is more detailed, the other one is more abstract, but both of them are equally valid. The same linear program can be represented by writing C1, C2, Cn, A11, A12, B1, B2, Bn, and so on, everything explicitly, or in a more compact fashion by saying minimize the dot product of C and X. What is C? C is a vector in Rn with coordinates C1, C2, Cn. What is X? X is also a vector in Rn with coordinates x1, x2, xn. What is the dot product of vector C with vector x? It is c1x1 plus c2x2 plus cnxn. So by writing C dot product x, we just have a more compact notation for the same objective function. Similarly, if we look at the constraints can be written more compactly using a matrix. Matrix A with m rows, n columns, coordinates aij. Matrix A applied to vector x must be greater than or equal to vector B. B is a vector in Rm, m-dimensional space, vector B1, B2, Bm. Greater than or equal means coordinate per coordinate. X must be in the hypercube 0, 1 to the n, meaning every xi is between 0 and 1, and x is a vector of Rn, meaning every xi is a real number. Thus, these are two completely equivalent notations for the same linear program. No one is better than the other. Depending on your taste, you can choose to write it in the first or the second form. It's two presentations for the same thing. Thus, if you have an integer program, you have a similar linear program that looks identical except for the last line, replacing the constraint xi integer by the constraint xi real number. The complexity changes drastically. An IP is NP-hard. The corresponding LP is solvable in polynomial time. So we have an integer program for vertex cover. Therefore, we can write the corresponding linear program. Every vertex u, the corresponding variable xu must be between 0 and 1. Every edge uv, we must have xu plus xv greater than or equal to 1. And the objective is still the same as for the integer program it came from. We now have a linear program related to the integer program for vertex cover. Now comes the crucial step. We are going to use this linear program to design a good approximation algorithm, finally, for vertex cover.